Hi, and welcome to this next clip along in the Thermodynamics series. This time we're going to look at the enthalpy of solution. So this is a slightly specific example which uses Hess's cycles, so the triangular methodology that we've seen in year 12 or AS chemistry, but it also incorporates the new lattice enthalpy of either formation or dissociation, depending on the value you're given. So we're going to look at this one, and we're going to use sodium chloride as the example. And as we know, sodium chloride will dissolve in water to produce sodium ions, or the sodium ions of sodium chloride dissolve in water to produce the dissolved ions, and likewise the chloride ions do that as well. This is not a direct reaction in terms of the energy and the process that's occurring there. What we have to do is, in a similar way to a Born-Haber cycle, is we have to look at the individual processes that are occurring here. And for solid ionic substances, what we first have to do is use the lattice enthalpy of a substance to create the gaseous ions. So remember, this was often the final stage of a Born-Haber cycle before you then took the lattice enthalpy to create the ionic solid you were looking at. And so we use the lattice enthalpy for this process. It will be an endothermic reaction because we're dissociating the substance. And then once we have those individual ions, we then have to solvate or hydrate both of these substances individually in order to create the aqueous ions. And these are what's called the enthalpies of hydration here. So once we have these values, the enthalpies of hydration, we would have an enthalpy of hydration for each of the ions, one for sodium ion and then one for the chloride ion. Once we have those, we can then calculate the question, or the top reaction that we've got here, which would have been what's regarded as the enthalpy of solution. Now, if we put some numbers into here, again, these numbers may vary slightly depending on which piece of literature you're using, but for the lattice enthalpy of sodium chloride, we would be using plus 771, and for the hydration enthalpies of the two individual ions, for sodium, we would be looking at minus 406, and for the chloride, we'd be looking at minus 364. Both of those are being exothermic processes. If we think about the sodium ion, first of all, and the chloride ion will do essentially the opposite of this. The sodium ion will associate itself with the delta negative part of water molecules. We would get an attraction between the delta negative end of the water and the sodium ion. A number of water molecules would go around the sodium ion in a similar way as you will see in transitional metal chemistry. A coordination sphere would exist around the sodium. The delta positive hydrogens would obviously point away from the sodiums. For chloride, this would be the other way around, and so the chlorides would associate themselves with the delta plus hydrogen. So that is making a bond here, making an electrostatic force here, and so that making of that bond is an exothermic process. And so you would see negative values for the enthalpies of hydration. Lattice enthalpy, when we dissociate, would obviously be positive because it's requiring us to supply energy to that system. And so if we were to be trying to calculate the enthalpy of solution for this reaction here, we would be going from left to right. So we'd be going from the sodium chloride to the dissolved ions, and we would have to process or proceed via an alternative route using Hess's law. So the enthalpy change of a reaction being independent of the route taken, meaning that the arrow for the lattice enthalpy is going in the correct direction. It's going down to these gaseous ions, which means we don't have to do anything to the sign, which means we can add the positive lattice enthalpy value, and likewise the two enthalpies of hydration are also going in the correct direction, so we could also add the minus values, obviously being the exothermic values, so these would ultimately become subtractions, but we are adding those processes together, and this being the sum of the hydrations here, giving us a kind of generic equation that if we have the lattice dissociation energy, we can simply add the relative hydration energies. So this will give us a simplified version if you prefer that. But numerically, what we will be doing here is taking 771, and once we've added all of this together, we would be subtracting 770, which would give us a residual value of only +1 kilojoules per mole. So the enthalpy of solution of sodium chloride is typically not particularly exothermic or endothermic. And so it's not particularly a driving force in the reaction. There's not a massive change in energy either way. But largely solutions are made because of an increase in entropy. So we had initially 1 mole of sodium chloride going to 2 total moles of ions on the right hand side. So that increase in entropy, when we look at in later clips something called delta S or entropy, immediately following this clip we see that this increase in entropy is something, and this increase in disorder is something which allows ionic solids to change to solution because of the number of particles increasing. This delta S value making the subsequent delta G value negative. As I say, we'll look at that in more detail in some later clips. But for now, this allows us to take lattice enthalpies and apply it to a real-world example here, where we have the dissolving of an ionic solid to make the relative aqueous ions via a Hess cycle. So thank you very much, and I will see you in the next one, where we will look at delta S, this entropy term we've just introduced here, and move that on to something called Gibbs free energy in the subsequent number of clips. So thank you very much, and I will see you in the next one.